Welcome to lab number 10. We're now into double digits. This lab is called AC LRC series circuit. So we're into AC signals, but actually, lab number 9, you had a triangular AC signal. So anytime the voltage changes, your voltage source changes, you have alternating current. But now we're going to use the kind of current that comes out of your wall socket. The wall socket current's 60 hertz, 60 oscillations per second. And in this lab, you're going to run anywhere from 500 hertz to 60,000 hertz. And it's amazing. Our little 850 universal interface has a signal generator in there that allows you to continuously change the frequency up to about 60,000 hertz. So we're going to run that through these three devices that we've studied, the resistor right here, then the capacitor, and the inductor. And it doesn't matter what order they're in the circuit there. And then down below, this is a symbol for a sinusoidal AC signal. And right here, this is voltage as a function of time. Remember, lowercase for all of your quantities, voltage and current, charge, are lowercase when they're functions of time, but then this is the maximum voltage right there, capital V naught, and then this is sine omega t, and omega is the angular frequency. And it's related to the frequency that you tune in on capstone by 2 pi. So 2 pi, the normal frequency, is equal to the angular frequency. And when you use a sine, you got to use angular frequency. Anyway, so that is the circuit right there. It's in series. And remember, when you're in a series circuit, the current is the same. So current comes out of here, goes back in here, oscillating back and forth. So up here it's going back and forth, back and forth, back and forth in those devices. But they're all seeing the exact same current. So current is the same in all three devices. All right. Now, when we study AC signals with an inductor, this is what an inductor looks like right there. It's a coil of wire, produces a B field in the circuit. And a capacitor, and there's a 15,000 microfarad capacitor right there. And over here we got a resistor. So when we have those three items in the circuit, each one behaves differently. Each one behaves differently. Okay? Now, a resistor is the simplest device. So the resistance, V equals IR. So you know V equals IR right there. So you can see the resistor is a constant, and the voltage and current are directly proportional to each other. So we say that the voltage signal and the current are in phase with each other. They have the same phase. So we're going to look at that in more detail in a second. So that is the simplest. And by the way, resistors, all they do is turn electric potential energy into heat and light. So it doesn't matter if they're coming in this way or they're coming in that way. All they do is they run into the material and convert their energy into heat and light. All right. Now, a capacitor, that changes the field on the plates by putting more charge on or taking the charge off, and then flipping the polarity. But in the whole process with AC signals, the plate's going plus, max, and then it goes down to 0, then it goes minus max, and then it goes down to 0, and just flip-flops back and forth. In the coil right there, the magnetic field is either going like in that direction, or when it changes over, it goes in the opposite direction. Okay, now an inductor, the current is 0 when it has a maximum voltage. And as you recall from Lenz's law, whenever you change the voltage, then you're going to get a back EMF. So it turns out that when you change the voltage drastically, there'll be a drastic change in the device. and it'll actually kill all the current. And all the field in there now is at a max, but there's no current flowing because there's the greatest change in magnetic field taking place. And when the greatest change takes place, then it will actually choke off all the current. So when the voltage is a max, then the current is 0. And we say when that happens, the voltage is ahead of the current. The voltage is ahead of the current because the voltage is a max when current is equal to 0. All right, so that's Eli in Eli the Iceman. So the voltage in an inductor is ahead of the current by 90 degrees. All right. Now, in a capacitor, when we apply a capacitor to apply a voltage to a capacitor, at first there's no field on the plates. So the current comes because it's easy to load up the plates with charge. So you got maximum current, but at that beginning time there's no charge on the plates, so there's no voltage across the capacitor. All right? So the current is a max when the voltage is equal to 0. Okay, that's the behavior of a capacitor. When you hook up a capacitor with a voltage V, in the beginning the current goes fast because there's no charge on the plates, and so across the capacitor there's no voltage. It has to build up to its maximum charge, and then there'll be a maximum voltage. Then when that happens, the voltage will be a maximum on the capacitor, but the current will be 0 because it can't take any more charge. So you can see the phase relationships in an inductor and a capacitor are more complicated. All right, and that's where ice comes from. The current is ahead of the voltage in a capacitor. So a nice way of remembering that is the line Eli the Iceman. Eli the Iceman. All right. Anyway, this is what the current looks like. When it goes into the capacitor, it is ahead. So in an inductor right here, the current is 0, so the voltage is ahead. And this minus sign means that the sine wave right here is shifted by 90 degrees into the future. So the voltage is a max before the current is a max by 90 degrees, which would be 1/4 of a period. Down here, the plus sign means that the current is first maximum when the voltage is 0. Okay, so this sine wave, if you move it back, it will be 90 degrees, 1/4 of a phase ahead of the voltage. It's all going to make sense in a second. I know just going through that is a little bit complicated. All right, so let's go ahead and look at the resistor. So the resistor, the voltage that you're going to put in the circuit is this voltage max sine omega t. And here's a resistor hooked up to that voltage right there. But you know, V equals IR. So I, as a function of time, is simply divide both sides by R, and there's your voltage function. See, they're both in phase. So when you plot them on the screen, you see here's the voltage right here, goes up to a maximum voltage, comes down here, goes to a minimum voltage, and then up like that. Well, at exactly the same time, you got the same behavior going on with the current. So the current maxes out when the voltage maxes out, and then it goes to 0 when the voltage is 0, and so on. So we say that the resistance is in phase with the current in a resistor is in phase with the voltage in the resistor. By the way, we're looking at the voltage in the resistor. Okay, they're both in phase. All right, let's go on to the next one. Next one is the voltage in an inductor is the change in current over time. Okay, the voltage in an inductor is equal to L, the inductance, times di dt. So we have to integrate this thing. So we're going to multiply both sides by dt and then integrate it to get the current function. All right, so this is the next step in solving this thing for the current. Okay, so we divide both sides by L, and we got our dt over here, so we're going to integrate the sine. And we integrate sine, we get minus cosine omega t, and remember, this constant right here is going to come out, and it's down here in the bottom. Now, here's the deal, and here's what we're studying in the lab. We're going to be looking at this quantity right here, and that's called the inductive reactance. Now let me go back to this one. So you see how we had R down here? So current equals voltage divided by resistance. Now this is just a sine wave, so that doesn't have anything to do with the units. There's no units here. Okay, so over here we got our voltage. Voltage divided by the frequency times the inductance. So that's acting like a resistance. So the higher the frequency, the bigger the inductance reactance, the inductance resistance. It depends on the frequency. And that's because of Lenz's law. Remember Lenz's law, if there's a big change in the flux, then you're going to see a corresponding change in the EMF that's induced in the inductor with Faraday's law. Okay? So this quantity right here represents the resistance of an inductor. All right, now we call that XL. So XL is the resistance of the inductor. So if you go right back here, you can see the similarity between the equations. But the thing is, now we got a cosine, so if we write the cosine like a sine, then the current is, remember Eli, the voltage is ahead of the current, so this guy here is shifted 90 degrees to the right. So let's go ahead and look at the phase now. So this is the circuit. We're just looking at the effect of an inductor when we hook up a sine wave. So this is the voltage like this, same as before. See that voltage right there. And the current now, so you see when the voltage is changing right here, then we get a maximum with a minus sign, a maximum current negative. All right? And then when the voltage is a maximum, then you see the current is 0. Okay, so up here the function is really changing a lot up there, so we get the most induction inside the coil, and it completely kills the current. So when you look at this graph right here, the voltage, when it's 0 over here, this is occurring earlier than when this is 0. So you see this voltage is 90 degrees ahead of that 0 value right there. Or you see when you're a max right here, you see 90 degrees in the future, this current is now going to be a maximum. So the voltage is 90 degrees ahead in comparison to the current inside the inductor, and that's because of the self-inductance that's taking place when the voltage changes most dramatically. And that's occurring right here. You see when the sine wave changes from being positive to negative, that has the biggest induction value, and it totally kills the current for 1 instant right there. All right, let's go and look at the capacitance now. Now, you know, with a capacitor, when you put the voltage across the capacitor, then it's real easy to charge up the plates at first, so the voltage in the capacitor is 0. So by Kirchhoff's loop rule, the voltage here plus the voltage here is equal to 0. Okay, and this is the equation right over here. So we're going to have a voltage sine wave driving the capacitor. And remember, capacitance is Q over C. So in order to get the current for this thing, we need to take a derivative. So I equals dq dt, and we take the derivative of this thing. By the way, we're going to multiply both sides by c, so we just get q all by itself. So dq dt is c times v, and then the derivative of a sine is a cosine with omega coming out again. All right, now, if you go back to the last one, remember we had omega t on the bottom. Well, here we got omega times c in the numerator. So this resistance is actually an inverse function. So you see up here, I put it down here. See, XC is 1 over omega C. So when you plug that in down there, it jumps up into the numerator up there. All right. And we got a cosine, so now we're going to make the cosine into a sine so we can compare things. And the plus sign means it's shifted to the left, and so at t equals 0, you see the current is a max. So when you turn it on, when you turn the sine wave on, starting from 0, the current is going to be a max because there's no charge on the plates. All right, and as the plates charge up, then you know the current goes down. You studied that in lab, and when the current is 0, then the voltage is a maximum across the capacitor. So you can see the current is ahead of the voltage. Remember, this is time over here, so this comes first and that comes second. All right, if you go back to the last one, see it's just the opposite. Notice we're not changing the voltage at all. So there's a voltage, there's a the blue line is the voltage. So it's always the same. We're relating everything to the voltage, and it's the current we look at in each situation. So now the current is ahead of the voltage by 90 degrees. So that's where that function comes from. So the resistance of a capacitor is 1 over omega C. All right, what does that mean? That means that when the frequency is low, the capacitor really has an effect on the circuit because you got enough time to charge up the plates. Whereas if the frequency is really, really high, then there's no time to charge up the plates. And so the effect of the capacitor in shutting down the circuit, remember a fully charged up capacitor is an open circuit. But if there isn't enough time to charge up the plates because the signal is so fast, then the resistance of the capacitor is low. So that's why the omega is down in the bottom. So as omega goes up, the resistance of the capacitor goes down. So we're going to study that in the lab. Okay, and so this is called the capacitive reactance, and again, it's frequency dependent. So this is XL. So as omega gets bigger, then the induction, self-induction goes way up because inductors love changing flux. Capacitors love full capacitor plates, and that only happens when you have low frequency. Okay. Now, the next video, we're going to talk about actually doing the experiment. So at this point, we're going to cut out of the background and then head on to the experiment. So over and out. See you in a second.